Hi, let's continue with Module 8, Verification of Renewable Energy Forecast with its second block, Verification of Deterministic Forecast. Remember that deterministic forecasts were introduced in a previous module. These deterministic forecasts are trajectories in the future for the variable of interest, but these trajectories give you a single value for this variable of interest for each and every lead time in the future. So an example, if you make a solar power forecast for 24 hours ahead, you will state, I believe that solar power generation would be of, let's say, 3.2 megawatt hours for this hour tomorrow. Looking at this forecast, visual inspection is actually a very good way to get started to develop some feeling about forecast quality. Basically, visual inspection is just about making plots. You want to plot your forecast, you want to plot the observations that were obtained a posteriori, and then you want to see if there seems to be a match or not. Obviously, this is a qualitative analysis only, but still, you can derive a lot of very nice insight about forecast quality. For instance, what do you think about these two forecasts? Are they good or are they bad? These two forecasts I refer to are for the same test case, the same wind power portfolio, but for two different dates. On the left, you have forecast issued on the 16th of November 2001 at 6 in the afternoon. And then on the right, you have forecast issued on the 23rd of December 2003 at noon. In both cases, the forecasts are with hourly resolution up to 48 hours ahead. And you can see on the y-axis, they are for power normalized. So the power value are between 0 and 1, but you may reinterpret 1 as the nominal capacity of the wind power portfolio. In these plots, I explain you, we show forecast and observations. Here the forecasts are shown with the bold black line, and the observations are shown with these circles and gray lines between them. So what about these two examples? On the left side, if you look at the forecast and the measurement, it seems it started well for the first 5-6 hours, but then there seemed to be a quite significant mismatch between the forecast and what really happened. The forecasts are way below the average level of power generation that was observed. Also in terms of shape, all the shapes of going up and down that we see in the power measurements don't seem to be there in the original forecast, that are quite flattish. In comparison, on the right side, if you compare the forecast with the measurement, the match is very good. The forecasts are going up and down to the right level and with the right timing. It has the right plateau here of no power generation. Then it's picking up again at the right timing and with the right slope. Then it's also giving the right trend for another drop, and maybe for the last 12 hours it's a bit off, but still it's very good overall. So if you were binary in your assessment, you would say this is a good forecast, this is a bad forecast. It might be a bit more complicated than that, but you see the starting point. By making this plot, we can really start developing a feeling about how good the forecast may be. If you were to push it a bit more, you will go with this visual inspection and try to look for certain features. For instance, since the errors in renewable energy generation forecast are most often driven by weather forecast errors, then you would expect some patterns we know from weather forecasting errors to be there also in the renewable energy generation forecast errors. Typical patterns are amplitude errors and phase errors. Let me illustrate this concept based on two other forecasts. We have, again, for the same portfolio, two forecasts issued on the 29th of March 2003 at 12 and on the 6th of November 2002 at midnight. Let's look first at the forecast on the left. If you compare the forecast with the black line, with the observations with the gray circles and lines between them, there seems to be a very good match, right? The level is right, it's picking up right, it's kind of peaking down right and also back to the right level. But there in the middle, even though the pattern seems to be quite okay, you see that the forecast doesn't go to the right level. So this is typically what we will call an amplitude error. It seems that the pattern is fairly right, but it's just not to the right level. In comparison, you have here what we call a phase error. Let's look at this forecast and see that it follows very well. The pattern is right. There's also going to be a drop in power generation and then a plateau again for the last day. So the pattern is quite right, but if you compare, see the drop here is at lead time, let's say around 22 to 24, but the actual drop in power generation actually happened 3 to 4 hours after what was predicted. So you have to look at it as an error in predicting, for instance, when weather systems are moving from west to east. They are coming from the west side of Denmark, and even though we know that these fronts are coming, these weather systems, we are not completely sure of when they're going to come or when they're going to go afterwards. Besides this qualitative analysis, obviously we can go a bit more quantitative. And for continuous variables, like we have here with renewable energy generation, but it can be some other variables, we can do this quantitative analysis by calculating a lot of scores and diagnostic tools. As a basis for that, we need to collect a lot of data. The data we need to collect is the forecast, obviously, the measurement, obviously, and you may also collect a number of extra explanatory variables. For instance, if you want to condition your quantitative analysis by some weather conditions. So for instance, you want to know if your forecasts are better when it's cloudy or not cloudy, if your forecasts are better when the wind comes from the west or when the wind comes from the east, etc. The best concept for any quantitative analysis when analyzing forecast is the forecast error. We calculate the forecast error as the difference between the measurement and the forecast. Look at the notations here. The measurement is for a time t plus k, and originally we made a forecast for this time t plus k, but at time t. So we have this notation t plus k given t. Consequently, we use the same notation for the error. This is the error for the forecast made at time t for time t plus k, or said differently, t plus k given t. The forecast error originally can be between the nominal capacity of the wind farm or solar power plant or whatever renewable energy device you consider, and minus the nominal capacity. Since obviously you have to consider the sign of this difference, you have a worst case where you predict nominal capacity, but what's really happened is zero production, and the worst case on the other side is just the opposite. That gives these two bounds. Now that we have calculated the forecast error, we may directly use it, but as we showed in the plots before, we might prefer to work with a normalized version, and a way to normalize readily would be to divide each and every error by the nominal capacity of the wind farm or solar power plant of interest, and this would give something like that. So the error for time t plus k given t is the error as we calculated before, so the difference between measurement and forecast divided by the nominal capacity. In that case, obviously, the error would be between -1 and 1 instead of minus nominal capacity and nominal capacity. Note that there are other ways to normalize forecast errors, but this would be the most standard and handy one. Let's look at some examples. We have seen the example of this forecast from before, and we want to calculate forecast errors. In a very simple case, let's look at 24-hour ahead prediction for this Klim wind farm, and this prediction 24-hour ahead is 18 megawatt. If you talk power, this would be 18 megawatt hour if you translate it to energy to participate in the market. The observation there is 15.5 megawatt. So if we calculate the error, measurement minus the forecast, we have an error of minus 2.5 megawatts. If you were to normalize the forecast error, this is minus 0.119 or minus 11.9% if you prefer. Now let's look at this example of a forecast. We have the observation too, so we can just calculate the difference for each and every lead time between the observation and the forecast. We represent it here, that's the corresponding forecast errors. 0 is the zero error case, and then it goes between minus 1 and 1. You recognize here on the x-axis the lead times. Since there was not much difference here between the forecast and the measurement, you recover it here. The error is close to 0. But during this period, with the phase error, there is a quite large distance between the measurements and the forecast. You recover it here. And then finally, for the last period, we have the right pattern, this plateau, for the second day of the forecast. But still there's a bit of a difference. So this translates to this kind of forecast errors. Now we're going to work with normalized forecast errors since it's quite easier. And since you don't want to look at all forecast, observation, and all forecast errors over a long period of times, then we need to calculate some summary statistics. These summary statistics will be called scores, and they are there to summarize different aspects of forecast accuracy. The most common scores include, and if you were to denote the lead time k that we'll use in the notation here, we would calculate first the bias. And the bias for a given lead time k, so you would collect all the forecast errors made in the past for this given lead time, so it could be the 1 hour ahead forecast or the 12-hour ahead forecast. For this lead time, you collect all the forecast corresponding measurements, you calculate the forecast errors, and then the bias would consist in averaging all these errors. So you have 1 over t, sum t equal 1 to big T of all the forecast errors. As you may expect, you would like this bias to be as close to 0 as possible, since it will tell about some systematic error you seem to be making with your forecast. Then imagine if your bias is 0, does that mean that you don't make any error? No, it just means that on average you don't make any error by just pulling them all together. Imagine the case where you would systematically make errors of +1, -1, +1, -1, etc. Your bias would be 0, but actually would make very big errors at each and every time. It's just that when you average everything out, it gives 0. So a bias of 0 is a necessary condition so that you can say later on that your forecasts were good, but it's not a sufficient condition to say that your forecasts were good. So this is why we look at some other scores that can give another dimension to the forecast accuracy assessment. The first one is the mean absolute error, MAE, and it's calculated as the sum of absolute values of forecast errors, also divided by the number of these errors you have here. In parallel, you have the root mean square error, which has the same basic philosophy, except that instead of taking absolute values of errors, you're going to take squared errors, you're going to divide by the number of errors you have under the sum, and you will take a square root of that eventually. Note that RMSE is used in a lot of fields to assess deviation from a trajectory or difference between a truth and some estimate, etc. MAE and RMSE are negatively oriented, so the lower the better. Obviously, if you have a MAE of 0, that means that you are making 0 forecast errors all the time. Same for the RMSE. If you have an RMSE of 0, you're making 0 error all the time. And as your errors are getting away from 0 error, MAE and RMSE will increase positively. There are obviously subtleties in the way we have to use these scores and interpret these scores. So for instance, since this is quadratic, while here we have absolute values, it's like it gives a different weight to forecast areas that are small and that are large. You simply, to see that, have to draw the function for absolute values and quadratic functions. Then you can see the difference between the two in terms of weighting the errors. Here are some examples for the period that we mentioned for Klim from 1st of July to 31st of December 2012. Forecast quality here is assessed with the bias that we just explained, the mean absolute error, and the root mean square error. They are all in their normalized version since using normalized errors. These scores are calculated as a function of the lead time. As I was explaining in the previous slide, for each and every k, each and every lead time, we collect the errors, we calculate the scores, and then we also plot them as a function of the lead time. The bias here is close to 0 all the way. As I was telling you, this seems to be a necessary condition, but this is not sufficient. Obviously, because our bias is 0 doesn't mean that our forecasts are perfect. We're looking here then at the mean absolute error, how it evolves with the lead time, and the root mean square error, how it evolves with the lead time. Note that I've added also a standard deviation of error, which is another score which is very close to RMSE, and here they actually coincide. On average, you can deduce what is the error of some forecasting method. So here it's for a given forecasting method. On average, you can deduce the error by looking at the MAE. So here, for instance, there's an average of 1.68 megawatt error between the forecast and the measurement. This is, since we look at absolute values, this permits to make some kind of a statement. This is not possible with the RMSE. We can compare the forecast as a function of the lead time and see that obviously the forecast seems to be better for short lead time, and it degrades steadily as the lead times get further. When we have calculated these scores, then it might be interesting to actually compare the score of a certain method, so the forecasting method we have used here, with some benchmark approaches. The point of forecasting is not to do well in absolute values all the time. It can be also just to do better than certain naive or benchmark approaches. We will introduce benchmarks in a further module, but the two benchmarks you need to think of here rapidly are persistence, so any forecast in the future is equal to the last measurement, and climatology, any forecast in the future is equal to the average of whatever we collected in the past. Then we can define a skill score. A skill score will give you a relative improvement over the score of this benchmark, for instance. A skill score can be written in this way. So SSC for skill score for a given lead time k is going to be equal to 1 minus the score of your advanced approach for the lead time k divided by the score of your reference approach or benchmark for lead time k. The skill score will always be less or equal to 1, and if you were to multiply by 100, it would be possibly expressed in percent. In this expression, SC, the score, could be the mean absolute error, could be the root mean square error, it could be something else. You should think of the fact that if we were to calculate this skill score, a skill score of 1 means that you have perfect forecast, since that would mean that this has to be 0. The score of your advanced approach being 0, this means that you have a perfect forecast. And obviously this can degrade and be below 0 if the score of your advanced approach is actually worse than the score of your reference or benchmark approach. Let's look at it here. We can compare the forecast we had from before to the case of the persistence and climatology as reference. We have these curves here where with the circles, this is the skill score versus persistence in terms of RMSE, and with these crosses, this is the skill score in terms of RMSE versus climatology. what we can see here is that we tend to reach a very high improvement versus this benchmark, so in the order of 50–60%, but not for the same range of lead times. You see that for short lead times, the improvement with respect to persistence are fairly low, even though we are improving steadily, while the improvement over climatology are very high. Then we go to further lead time, we see that it tends to be the opposite. It's very easy to improve a lot over persistence, more than 50%, but then it gets more and more difficult to improve over climatology. So somehow if you were to combine these two these two reference methods, you would end up having this kind of improvement, this kind of skill scores of your advanced forecasting method versus this combined reference. Finally, one may use some diagnostic tools that are based on error distributions. Remember that we've been collecting a lot of forecasts, a lot of measurements, and now that we had that all together, we calculated scores as summary statistics. If they are summary statistics, that means they cannot give you all the information about the actual forecast quality. And you may be better off by investing in a full analysis of the error distributions, and you will see that it could tell you quite more. These are examples for the same period, 1st of July to 31st of December, of error distributions that were collected, for instance, for 24-hour forecast, so all the forecasts made for lead times of 24 hours, and 36 hours ahead forecast, so all the forecasts that were made looking at 36 hours ahead. The forecast errors here are summarized by histograms, so with positive errors and negative errors. Remember that the errors are normalized. And by looking at the shape of distribution, you can see, for instance, that this distribution is much sharper, it's quite narrower than the other one. So that means that you tend to make more often small error and less often large errors. If you compare here with this one is not that sharp. So it means that you make less often small errors and more often large errors, as shown by these tails. Eventually, for risk management purposes, you may be interested in reanalyzing these distributions and, for instance, looking at certain quantiles of these distributions. So for the test case of Klim and for the same period, we can look at how we have errors for which 90% of them are less than a certain level. So this would be what is shown here. Or you can have some other plot where you look at the percentage of prediction errors that are being greater than a certain level. So for instance here, 20% of the nominal capacity. By looking at these different plots, so this is here as a function of the lead time, and we have here a plot for the frequency related to a certain threshold. We have a plot here for a level of power related to a certain frequency. By analyzing this number, we can understand what are the frequency and magnitude of certain type of errors and compare in detail different methods. Thank you very much. I would like now to invite you to use the self-assessment quiz to check your understanding.